Okay, I think we can start. I will share the screen and then I will start to discuss PEFT method. Probably. Okay, I'm gonna say that fine-tuning large language models has traditionally been a resource-intensive task, and it's required a substantial computer power and memory. And to address these challenges, people developed parameter-facing fine-tuning, PEFT in short naming. And this technique is focused on adapting models with minimal parameters updates and enabling efficient use of resources. And here, I opened a paper to show you that we have a lot of techniques in PEFT methods. So all these techniques divide to around 4 or 5 groups. And here are main of them. You can see in the middle of visualization that there is a reparameterization-based method. It is a method when we use a small subset of parameters using low-rank matrices or something like this. Also, we have additive fine-tuning when we methods when we append learnable embeddings probably or some tokens to input sequence. Also, there are adapters. It's lures which we add to model and then we fine-tune it. Also, there is methods like bitfit when we tune only bias of the model. There are a lot of techniques in this PEFT methods, but we will discuss it more deeper on Friday. But today I want to show you a code of prompt tuning and low-rank adaptation. In short name, and it's LoRa. And probably LoRa right now it's the most popular technique which people use to tune a small subset of parameters in the model. And usually people know only this method, but we will dive into a lot of techniques in PEFT methods, and we will discuss which methods are better than others. Probably LoRa, it's one of the best methods nowadays, and it has got a lot of important changes and options which we can use. But I think we can choose PEFT method beside on the task we want to solve, and we will discuss it on Friday. Right now, in this seminar, we will explore prompt tuning. It's a lightweight method that appends learnable embeddings to input sequence to grid model behavior. And LoRa, it's low-rank adaptation, a technique that modifies only a small subset of parameters using low-rank matrices. And we will learn how to apply PEFT techniques using Hugging Face PEFT library and custom implementations. Challenges that we have in standard fine-tuning, it's memory and compute costs. Fine-tuning all model parameters for large models like GPT of the third version or Llama can require hundreds of gigabytes of memory, And because of this, 2 weeks ago, when we fine-tuned Llama on the lesson, we used LoRa to tune on the small subset of these parameters. Also, if we update all parameters, increases the change of overfitting, especially with small data sets. And in this case, if we have a small data set, it will be better to fine-tune decoder-only model with LoRa, for example. Also, there is task-specific resource reusability. Standard fine-tuning makes it harder to reuse the pre-training model for other tasks, and we can use PEFT for this. Let's discuss advantages of the PEFT method. For the first advantage, I would name that by updating only a small subset of parameters, PEFT significantly reduces computational overhead. Also, PEFT methods can be applied to existing pre-trained models without modifying their core weights, and fine-tuning becomes resource constructed environments like laptops or single GPUs. And we can name that the third advantage is scalability. We can discuss. Okay, let's start with the code, and I will explain what we have here. So we will use CUDA for the training today, because we will upload 7 billion parameters of Llama, and if we will not use CUDA in the environment, it will be really heavy and slow. Also here, we will use gradient checkpointing. Here we can see code blocks that enable us to use checkpointing. And let's discuss what's it. Gradient checkpointing is a memory-saving technique used during the training of deep learning models, especially large-scale models like transformers. It trades memory usage for computational overhead, enabling the training of models that would otherwise be too large to fit into available GPU memory. And gradient checkpointing works like on the first stage of its pipeline. We can name that during propagation, gradients are calculated for each layer by storing the intermediate activations, outputs of forward passes. These stored activations are required to compute gradients for the earlier layer. So for very large models, storing this intermediate activations for all layers can exceed available memory. And instead of storing activations for every layer, checkpointing stores only a subset of them. For layer without stored activations, the forward pass is recomputed on demand during back propagation. So there are advantages like memory efficiency and scalability, which means that enables training deep models with more layers or higher parameter counts without requiring extensive hardware resources. And also there are trade-offs of this method because forward passes for non-checkpointed layers must be recomputed during back propagation, leading to additional computational overhead. The time cost depends on the number of layers being computed, and gradient checkpointing requires careful selection of which activations to save and which to recompute potentially increasing implementation difficulty. So we can use it like here. We can just apply a method in Hugging Face to use gradient checkpointing, and then we go into prompt tuning, and in the beginning we can discuss what is prompt tuning, and then we will look through all the examples that we have in the code. So it's a technique where learnable embeddings are prepended to input sequences. This embeddings acts as guides, steering the model's pre-training knowledge towards specific tasks. And only the prompt embedding are updated, leaving the model weights untouched. Also frequently used in classification, text generation, and domain adaptation tasks. The model's embeddings layer is modified to include additional trainable vectors. During training, these vectors are optimized alongside the task-specific loss function. At inference, the trained prompts are prepended to inputs for task-specific predictions. So I think that there are some advantages of using these methods. If we will use prompt tuning, we can use on inference different prompts in one batch. And for some specific task, it can be more, it can be better to infer in a whole batch, and we will not use different inferences for different tasks. Here we loaded model, and I did it before the lesson because it loads a little bit slow because of its weight, and you can see how many files it's loaded. So maybe we can see how long was downloading. It's kind of 2 minutes for uploading all the model. And here in this code blocks, we can see how prompt that we want to tune. Okay, we can tokenize prompt, and then we can infer our model. But I think it is a little okay. Here we can calculate loss for prompt that we encode, and then pass it to model, and we can see loss of cross entropy loss, this value, and print it. But let's implement prompt tuning, and let's dive a little bit to this method. So here we have a class for implementing this method, and it's adds trainable embedding that dynamically adapt to the tasks. And we can see it here that we implement a parameter for updating the tasks, and also we the first num prompts use the original pre-trained embeddings, and in the end it combines learnable and original embeddings for seamless integration. You can see it here. We just concatenate learnable prompts and original embeddings. And we will learn on only this prompt that we insert in the beginning of the sentence. Here you can see how we can use it. Okay, let's run it, and let's run these blocks. I see what will be here. Okay, here we just test this updating embedding layer on our model. We let me see. We insert to test input IDs our class that we implemented, and then we pass embeddings of the model to the class, and we can use it on forward method. Then you can see here how we will use it. No, not this one. This one. So when we will pass it to this code line, we will go for the forward method, and then we will pass this input IDs that we here, this input IDs to our model, and it will train our model, and we will require gradients to go only on our prompt that we added. So here we tested that no asserts are enabled, and we can use whole model for the training. In this line, we switch our embedding layer in the model to our class, and then we can use it in the okay, let's import to QDM. It's a progress bar that we will use here, and we can see that our loss is decreased, and our model is learn our information that we want to. We can see that we train only learnable prompts while reading the models, why it's also matters the difference between predicted and true token probabilities, and we train stops once the loss reaches a target value. So when we will reach this threshold, it will stop. Here you can see that our loss decreased very intensive. So here we can use our model and see what will be what it will be. It will generate, and also how does it work. At home, you can change the prompts that you tune, or maybe switch some keeper parameters of the training and see how does it going. But here we have a second method, and it would be better to reload our model to use PEFT method. So
can we see how did this prompt change? What's the difference in the prompt?
what do you mean?
So we, I mean that we have the learned prompt now, right? So a different prompt.
No, we okay. We added. Let's look into this class. We added prompt and enabled gradient on the embeddings, on the initial embeddings of the lawyer, and which we had in the model, and we we apply gradients to okay. We apply backpropagation only on this prompt that we added. That's it.
Oh, okay.
And you
But-
can, yeah.
So, I mean, this training that we had, right, with some achievement to the low loss, what did we train exactly? So we trained these parameters that we added to the prompt.
Yeah, you can, okay, I will show you on the visualization.
I mean, how does it help? There are some parameters, right? I mean, some numbers potentially from the same space uh, from embedding embedding space, right?
You can look at this. You can add task prompts like
Mhm.
we added to our model, and we okay. You can imagine right now that we added this A to our embeddings of the model, and we tune only this embeddings in the model, new embeddings, but we freeze old one. And when we will use different tasks, we will have new embeddings for new task. And then when you will infer your model, it will look only on this trainable embeddings and predict next token based on only these embeddings that you used.
So some task specific.
Yeah. So you can imagine that you can use it, for example, in chatbots. If you want one task, okay, when you want to generate chat, for example, on the divides groups of people. For example, for children, it would be their own embedding space. For the adults, it will be second one, and for elder people, it will be the third group. You can infer it in the same time in one batch, how you can see on the visualization, and it will works. But you need only age of the person with whom you communicate in the moment.
Okay, thank you.
Yeah, maybe this method, it's sometimes you need to have initial task to use it. And for example, that I explained to you right now, but probably if you use one large language model that we have nowadays for all the tasks, for the math task and for the code generation, you can use just LoRa that we will explain how it works right now. But now I will reload my session to reload the model. Okay, I will show you how this LoRa works. And how I said, it's a technique that fine-tunes only low-rank approximations of certain model layers. Instead of updating all parameters of, imagine that this is all parameters and this is matrix of all parameters in the layer. You instead of updating all parameters, we can introduce trainable matrices of A and B matrices that are just the layers outputs. Significantly reduces memory and compute requirements, and also often applied to attention layers like query, key, and value projections. Let's see, did we loaded our model?
What do we do then? So we trained low rank approximation parameters, right?
Yeah.
But then do we convert it back to the full model size somehow, or we continue using this small model kind of low rank?
Okay. So when we train these low rank approximations, we can use backpropagation method on the low rank, and it will works. It's the significant change in LoRa method, because before this method, people thought that we need to go to the initial metrics and do backpropagation on this big metrics, and then go to low rank adaptations and train it. Do forward path there and go back to the initial metrics to do backpropagation. But in this method, we don't need to do it, and we can don't use metrics and don't save it in the RAM. And because of this, we will not spend our resources for storing these metrics. But in the end, when you trained this model and you want to infer it on your tasks, you can use these metrics and infer it in low rank approximations. But if you want merge it with initial weights, you can do it. You can do operation that will go to initial metrics, and your lower ranks metrics will reverse to the big metrics. Then you will summarize initial weights of the metric of the layer with these tunable weights that you trained, and then you will store it like a whole model. And LoRa has really good option that we can merge different LoRas that was trained on different tasks, and maybe in natural language processing we don't use it so for all the time, but in the computer vision, when people train diffusion models on image generation, they use this option a lot, and usually they train LoRa on generate, for example, fingers on the image, because it's really hard to train diffusion from the beginning, to train fingers of the people. Then they can use one LoRa for hands of the people, for example, then train another LoRa for heads of the people, for example, and in the on the inference they can mix these metrics, these LoRas, for example, in different weights. I mean that they can multiply one hyperparameter, and then it will work. So if you use only half, like for example 0.5 as hyperparameter, it will not rely on the final result as you multiplied one for all the weights of the LoRa. Did you get this or no?
Yes, thank you.
Okay, amazing. So let's see, did we load? Yeah, we load our model, and now we can see how does it works. In the beginning, we will use PEFT library from transformers. And here you can see that we, we used get PEFT model function, and we can calculate trainable parameters of the model right now. Also, we can calculate all parameters that was in the model, and you can see that we train only a small part of our model. Also, yeah, you can use this method for train your model, and you can learn a little bit more about this library on Hugging Face site. Yeah, here. And here you can see installation of this library. Then you can see how you can use all the prompt-based methods, also LoRa and others, and also they implemented merging for models, and we will discuss it on the next no, it's merging for PEFT methods. So here they implemented how you can use different adapters on different tasks and then merge it in the one model. And it's really useful in the real projects. You can use different adapters on different tasks. Yeah, but now we will learn how to use LoRa in from PEFT library. And let's, yeah, okay. Let's upload model and enable gradient checkpointing here. I will explain you what we have in the LoRa class here. We'll try to implement it. In the PEFT library, they have implemented classes for LoRa method by themselves, and you can see a raw code in their repository. So yeah, you can see LoRa config, and you can see how to use it really easy. You just you can just convert your base model to the PEFT model, and then create create train loop for this. Let me see. Okay, if you will have issues with this, I have my own code for you can just go to our lesson which we had 2 weeks ago, and see implemented code for LoRa. We used LoRa for the training, but here we will implement this method by ourselves. So here we need to implement metrics that will reduce the input dimensions to rank. Then B metrics that will project back to the original dimensions. Then we will combine the original layer output with low rank updates, and then requires fewer trainable parameters, making it deal for large models. Okay, we can run it. and run this code, which test LoRa, are implemented for LoRa for all the tests in the code. So we focuses, let me see. Yeah, here we focus on attention projection layers, on projection of query metrics and key metrics and value metrics, and also we allow specific components of the model to be fine-tuned without modifying others. So we can see right now in the code how we did it. We just converted to LoRa class our models, LoRa's, I mean, from our model. And yeah, we can see our config of the model. How does it look like? So we will train only this projection, this one, and this one. We will not use, we will not do back propagations on other layers, but we can do this if we will choose these layers also, but right now we don't want to do it. So, and here we verify that the gradients are correctly computed for LoRa adapters, and ensures that the adapters are contributing to the model's updates. Then we can load a dataset from Hugging Face. And train this Hugging Face trainer like we did 2 weeks ago. So, and we can mention how decrease our loss function. It's a little bit waving, but I think it's okay. It will go down in the end of the training. Okay, weird. Here, okay, I didn't see this code block in the initial notebook, but okay, let's discuss what is going here. I see that we just we don't do anything besides we did in the beginning of the lesson. We just test what will be if you will tokenize prompt and then generate tokens for this prompt. Yeah, like after regression task. Okay, we will test it after our model will trained, and let's wait for 1 minute for this. And also in this task, okay, just home assignment, I think, for you, or maybe author of this notebook didn't delete it. I don't know. Okay, if you want, you can do it at home, but I think it's not really important for our topic. Let's I think it was really quick, and we can discuss more information if you want, but let's summarize what we explored. Prompt tuning is lightweight fine tuning by editing learnable embeddings to input sequences. LoRa is efficiently adapting attention layers using low rank matrices. And what's wrong? Okay, I will see what was the issue of this. Let's generate output of continue on this of this prompt. Okay, we see that okay, it's pretty I can't say that model generated something weird. I think it's okay. And we can mention that loss of the model decreased, but I don't know what was the issue. Maybe in the evaluating part. In train loop. Okay, I will see what was the issue, because I didn't implement this notebook, and maybe it's a little bit strange for me right now to see this issue. It's an irregular issue, but maybe because of the implementing by ourselves something went wrong. But okay, it's trained for 100 steps, and it's okay. Do you want to discuss some more methods of PEFT, or we can end our lesson and then we will see on Friday. I will have long presentation of instruction tuning and PEFT methods, and there will we discuss all the groups that we have in PEFT and how does it work. Also, we'll discuss some more PEFT methods than in this notebook. But also, it's really good to explore this documentation of this library. It's really, really good, and there is some more methods that we implemented. Here is IA3, and you can see how does it work. But I think I will have this method in the presentation. Yeah. Do you have some questions?
No questions. Very interesting topic today.
Yeah, it is. Maybe you want to discuss something else, because it was really, really fast, and I'm not sure. Did you get all the important things in this method or no?
Yeah, maybe we can have some discussion on Friday.
Yeah, okay, it sounds good. Other people, what do you think?
I agree.
Okay. So thank you so much for this short lesson. It was really quick. This notebook I uploaded in GitHub repository in 9th week. You can see it here, and also you can find slides for our lecture. So that's it.
I have last questions about the homework.
Yeah.
So basically, there is submit multiplicative attention and additive attention functions in the contest. And then, of course, there is no contest. And Radoslav said that he will create one. So are we supposed to do that in contest? Wait till he provides the link?
No, okay, in the beginning, I thought that you will just send me this notebook, and I will see what did you did. But he wants you to save this dict to CSV, and the contest will you will submit this dict, and the contest will get the value on the test split of the metric, and then you will get the result. What was did you train this good or no? If you want example how to save this dict to CSV, let me know, because I deleted it was the last code block in this notebook, and I deleted this. But you just need to implement all that you have here and train the model and save the results. That's it.
In CSV format.
Yeah.
Okay.
Yeah, I can right now. I can when we will stop the lesson, I can send code block how you can save results to CSV file. I don't think that it's a really difficult code block, but maybe you need the.
Yeah. I mean, you can do that. Like, it will save time if it's ready. Why not?
Okay.
Yeah, I also don't think it's difficult. Yeah, but if it's ready, yeah, let's do that. Thank you.
It works like on the Kaggle if you participated in in if you participated in some projects on Kaggle, it works like here. You will just submit a CSV file, and it will measure the metric on the test split.
Okay.
Here, yeah.
Got it. Thank you.
Any questions?
No.
Okay. So if nobody have questions, we can stop the lesson and have a good evening.